talk about transition method phosphorus trisulfide, which will be the focus of this presentation, and 3 compounds. And then here I will discuss mostly our collaboration with the experimental people. And in the last section, I will discuss more the theory part. So this is a simple 1D Ising model. And this problem was given by Lenz, who was a PhD advisor of Ising. And he found that there is no phase transition at finite temperature in 1D system. And after that, Ising didn't publish again. In 2-dimensional systems, Onsager found that there is a phase transition at finite temperature. And he got a Nobel Prize for his famous Onsager relation, not for this solving this 2D Ising model problem. So there have been several experimental confirmation of 2D Ising model. And there is this famous Mermin-Wagner theorem, which says that there is no continuous symmetries cannot be spontaneously broken at finite temperature in dimension 2 or less. And these people have worked on this theorem independently. And so this XY model or Heisenberg model corresponds to this category. If you focus on the XY model at 2 dimensions, there is no breaking of symmetry, so there is no finite magnetism. But the correlation function decays algebraically at low temperature, not exponentially, as in 1D case, for example. And because of this DKT transitions, Kostelis and Daulas got, as you know, 2016 Nobel Prize in physics. There have been several experimental studies try to confirming this DKT transition behaviors. Helium superfluid, superconducting thin film, Josephson junction array, and ultra-cold atomic gases. But Tony Leggett said that as far as I know, no system currently exists which will permit tests of all the static and dynamic behavior predicted of the DKT theory. So to summarize this first part of my talk, in 3D, as we know, phase transitions, there is phase transition at finite temperature independent of the kind of the Hamiltonian, the discrete Ising model or continuous XY or Heisenberg model. And 1D, there is no phase transition at finite temperature. But 2D is fun. It depends on the kind of symmetry. In 2D Ising model, no phase transition. And in 2D Heisenberg model, in 2D Ising model, there is finite phase transition at finite temperature. And in Heisenberg model, there's no phase transition. In XY model, there is so-called DKT transition. So, but in reality, there is no perfect ideal Ising, XY, or Heisenberg systems. So Heisenberg model plus slight easy axis anisotropy will, at very low temperature, result in Ising-like behavior. And also Heisenberg model with slight easy plane anisotropy will finally give us XY-like system at low temperature. And in real materials, and also in any real systems, there will be such a small anisotropy, and it will arrive at some phase transition behaviors. So let me introduce these class of materials. Since the publication of this back-to-back 2017 papers on 2D ferromagnetic materials, there have been a surge of studies on 2D magnetic materials. But before that, there was earlier studies on 2D antiferromagnetic material, FePS3. So transition metal phosphorus trisulfide forms a honeycomb lattice by these transition metal ions, and then they are surrounded by sulfur ions, and there are these peaks. And they're stacked in this monoclinic structure. Interestingly, their magnetic ground state depends on very sensitively on the transition metal ion. In manganese compound, it forms like the nil ferromagnetic order, nil antiferromagnetic order inside in the plane, and the neighboring layers are ferromagnetically coupled. And for ion compound, it forms a zigzag antiferromagnetic structure, and the interlayer coupling is antiferromagnetic. And in nickel compound, the in-plane order is zigzag like chains, but out-of-plane order is ferromagnetic. And people say that this manganese compound is described by Heisenberg model, and ion compound by Ising model, and nickel compound by XXZ or XY. And so there is some rich physics in this 2D antiferromagnetic material. So this is the electronic configuration. The 10 3D orbitals under is split into these 5 and 5 majority spin and minority spin orbitals. And again, it's EG doublet and T2G triplet, but under octahedral environment, this triplet further splits into 1 and 2 singlet and doublet. And in the case of manganese compound, it's D5, so the nominal spin is 5. And in the case of ion compound, we have 1 electron in this doublet, and so the spin value is 2. And in the nickel compound, we have 3 electrons, and the spin value is supposed to be 1. So let me start with this ion compound, which has been believed to be Ising-like system. So this is the susceptibility measurement data of a bulk ion compound. And this chi-parallel is the susceptibility along the outer plane, for the field along the outer plane direction. And this perpendicular is for field along the in-plane direction. And if you lower the temperature, then the ground state is along for the spins aligning along the outer plane direction. And because of that, the susceptibility along the in-plane field is larger than that for the field along the outer plane direction. Because if the spin is aligned like this, then the in-plane field will easily change the magnetic moment, but outer plane field is hard to flip those spins or make this actually. What happens when you apply strong outer plane field is that they change the spin polarization to be along in-plane direction. So yeah, but for weak field, the susceptibility along the outer plane direction or the ground state aligning direction becomes very small. So it's like Ising-type system. To measure the magnetic property of few layer or monolayer ion compound, one cannot use conventional methods for bulk compounds. By the way, this is an antiferromagnetic system, so one cannot use mode or speed. And also, because this is monolayer or a thin layer sample, one cannot use susceptibility, conventional susceptibility measurement or neutron scattering method. And so our experimental colleagues adopted Raman spectroscopy. Recently, there has been some development on the susceptibility measurement of 2D systems, but it's not, it has not been common so far. So for ferromagnetic 2D materials, they used MOOC, magneto-optics Curry effect, to confirm the magnetism in these 2D systems. And this is the Raman spectra. It's a function of temperature for both system. And around phase transition temperature, there is a strong sharp peak appears around the phase transition temperature. And they observed this a similar thing even for monolayer system. And our colleagues did the measurement for both all the way down to monolayer system. And this phase transition behavior reflected in the Raman peak, it persists down to the monolayer sample. So in non-magnetic system, the unicell has 2 transition metal ions. And in magnetic system, because of this zigzag magnetic ordering, the unicell doubles. And so, the Brillouin zone becomes half size. And the phonon that was originally not at the gamma point becomes the gamma point phonon, which we believe is detected by the Raman spectroscopy below the transition temperature. Right. And let's move on to the nickel compound. So this is the energy splitting diagram for trigonal distortion. And so nickel has 2 empty states, EG states. And so this is the projected density of states to nickel and sulfur states. And this part, this shaded area is from these EG states. But you also notice that there is a significant fraction of this sulfur weight here in the conduction band minimum region. And our calculated optical absorption spectra explains quite well this data. And because of this sulfur weight here, what happens is that the spin density doesn't just stays around nickel, but it's floating around the interstitial sulfur region as well. So this is the isosurface plot for spin density, spin up and spin down spin densities in this nickel compound. So the nickel ions form honeycomb lattice, and the spin density is also on these sulfur ions. So if we project the spin density to nickel ions, is 1.24 of a Bohr magneton, but nickel ions, but these sulfur ions has a non-negligible fraction of spins. There has been some puzzle in the experimental side. So there was a neutron scattering study which reported the spin value of 1.05 Bohr magneton, but susceptibility measurement reported significantly higher spin moment, two boromagnetons. And maybe we could understand this part of this frequency by this way. So neutron scattering may measure the spin moment localized at nickel ions, so this small value. But the susceptibility may measure everything together. So if we add these spin contribution dispersed in surface ions, then the spin polarization may increase from 1.24 to 1.54. And yeah, and if we add some quantum spin effect, because S square is square root of S times S plus 1, it may increase this value a little bit. I don't know. So then we may understand the discrepancy between part of the discrepancy between neutron scattering and susceptibility measurement. So I'll come back to this picture later. And let's move on to the Raman measurement of nickel compound. So they did, our collaborators did Raman measurement using this setup. So light comes in and it is reflected vertically, and that they can change the polarization of incident light and also change the polarization of the measured light. And so they used two different setups, XX and XY. XX means that these two polarizations are the same, and XY means that they are orthogonal to each other, which are these black and red curves. And the upper curves are at high temperature and the lower curves are at lower temperature. And so because of what people call quasi-elastic scattering, which is an interaction effect at low temperature, these signals are gone. And important thing is that there is this P2P, which is one peak with which is one peak at both these two different measurements, but it splits into slightly splits into two peaks for these two different measurements at low temperature. And there is this Fano-like continuum discrete spectrum coupling. So we did some DFT plus U frozen phonon calculation to explain these peaks observed in experiment. And we could explain that this splitting in frequency is closely related to magnetism in this material. So we calculated the phonon frequency, assuming that the magnetism is like zigzag chain-like, and also assuming that the magnetism is like Neal type, AB, 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 like type. And there, when we assume the zigzag type, there is a finite splitting between these two peaks, whereas when you assume Neal type magnetism, there is no such splitting. Although this splitting is bigger than the experimentally observed one. So they changed the number of layers and did the measurement at different temperatures. We do these two different experimental setups. And then they found that the TC, transition temperature, where the two peaks split, depends strongly on the number of layers in this case. Whereas in the ion compound, it didn't depend much. And moreover, so this is the splitting of the P2 peaks for bulk and all the way down to monolayers. And they found that there is no peak splitting for monolayer sample. And so they interpreted this result as that, so monolayer nickel compound is a truly XY-like system where there is no magnetic phase transition. And actually they include, me, because These are my experimental collaborators. This part is very short. So they did also the Raman measurement of manganese Heisenberg-like system, and we did calculation to match to interpret this Raman spectrum. And they observed the phase transition all the way until, so they found the peak which shift its position as you go below the transition temperature, and they observed that phenomenon all the way up to 2 layers. But monolayer, the signal was quite noisy, so we were not able to conclude anything from the experiments. Okay, so in order to explain these experimental results and also previous experimental results, we did first principles calculations on the electronic structure of this compound. And the model, which was constructed based on our first principles calculations, is like this. Our model has intra-layer exchange terms, interlayer exchange terms, and single ion anisotropy. And these J, K, and D's are not numbers, but they are 3x3 matrices, which can handle the anisotropy. And so our model has very large number of parameters, and for 2D, for studies on 2D magnetic materials, maybe, which is more complicated than the other systems that people studied. Usually the parameters are less than or equal to 10 parameters. So we calculated the total energy of bilayer this compound for various magnetic configurations. And from that, we extracted the parameters in the model. And we confined the spin directions to study the anisotropy. And we used these 22 magnetic ordering patterns per compound and 6 linear directions. And this is part of our results. Our calculation reproduces very well these magnetic ordering patterns, the ground state magnetic ordering patterns of all 3 compounds. And based on our magnetic model, we did Monte Carlo simulations to study the phase transition behavior. And so we included dipole-dipole interactions and also the orbital polarization for ion compound, which is important. And we studied the thickness dependence and the magnetic susceptibility, heat capacity, and the transition temperature. And let me show you the results for manganese compound. Actually, yeah, these are the first principles calculation result first. So the intralayer exchange interaction parameters are like this in MEV unit. And interlayer exchange interactions are very small in comparison with the interlayer ones. And the magnetic anisotropy energy comes from small. So the single ion anisotropy prefers in plane, easy plane anisotropy. So these are lower in energy than along the z direction. But dipolar anisotropy prefers out of plane direction. So the interaction between dipole, magnetic dipole-dipole interaction. Because in the honeycomb structure, from what we learned from undergraduate electricity and magnetism class, is lower in energy to have up and down spins on different sublattices. gain from the dipole-dipole interaction. So that's why the dipolar interaction prefers the z direction. And so in the end, we have small easy axis anisotropy. And this is the results of our Monte Carlo simulation. If we don't include dipole-dipole interaction, then the susceptibility looks like that. And at low temperature, the y direction is the minimum. So the high y becomes the smallest, whereas in the experiment, the chi z is the smallest at low temperature. And when we include dipole-dipole interaction, we can explain the experimental behavior. And our calculated Newton temperature is very, very close to the experimental value. And in the case of ion compound, right, again, the interlayer interactions are very small. And here, so this is the isotropic part, and this is the anisotropy contributions. And the strongest anisotropy comes from this LS coupling, and it strongly prefers the out of plane directions, which I will discuss in the next slides. So the anisotropy is quite large, 20 MeVs, which is quite large. And so this is the electronic configuration, the majority spin and minority spin. And here we have one electron in this doublet. And then it can spontaneously break the symmetry, and it can have some finite angular momentum. But in order to see this from first principles calculations, one has to be very careful in setting up the initial occupation. Otherwise we will not be able to see this behavior. So the previous studies didn't have this orbital angular momentum physics, and so the anisotropy reported previously is almost 2 orders of magnitude smaller than what we find here. So each ion can have angular momentum upward or downward, out of plane direction. And this figure shows, so our constraint calculation where we change the direction of spin, and the theta is the angle from the out of plane directions. And depending on these two different configurations, orbital angular momentum configurations, the energy varies like this. And while doing this, we have calculated the local orbit projection, the atomic orbital angular momentum of each ion, and the z value doesn't change much. So the orbital polarization stays almost out of plane always, direction always. And the in-plane part is small. And so we find that these lambda coupling constant is -10 MeV, about roughly -10 MeV. And this sign agrees with Hund's third rule because it's more than half-filled system. So the L and S tends to be anti-aligned. I'm confused. It's more than half filled, so they should be aligned or anti-aligned. No, sorry. Yeah. Yeah, I'm not sure about this. Okay, maybe we can come back later. So the orbital degrees of freedom is very important in understanding the physics in this ion compound. And yeah, so LS coupling is quite necessary, and this coupling constant and also the Néel temperature agrees quite well with the experimental value in comparison with previous theories. So here we compare the susceptibility, bulk susceptibility of the bulk material, theory and experiment. And you can see that if we don't allow the fluctuation of the orbital angular momentum, then we significantly underestimate the susceptibility. And only when we include that, qualitatively agrees, the behavior qualitatively agrees with the experiment. And from experiment, they found that there is almost no dependence of the T-Néel to the thickness, which actually agrees with our calculation. For nickel compound, so this is the interlayer exchange, isotropic part of the interlayer exchange interactions. And this is the interlayer exchange interactions. And you could see that this interlayer exchange interaction is not negligible. It's almost 1/3 of the intralayer exchange interactions. And so I'll come back to this later. And magnetic anisotropy energy, for this, there is no one big dominant term, but small pieces contribute each other. The single ion anisotropy and the intralayer exchange interaction and the dipole interaction term as well. Okay, so this K3 and K4 is these openings, which in distance is longer than these K1 and K2 terms. But why they are dominant? So it's related to this dispersed spin on the surface ions. So if we measure the distance from one transition metal ion to the interlayer transition metal ion across two surface ions, then their distances are almost the same, not the linear distance, the direct distance, but these distances for these three pairs, for these three, for these, all the hoppings are more or less the same. And as you can see, the spin at the surface ion increases as we go from manganese to nickels. The reason for that is because as you go to higher Z number, it becomes more and more electronegative. So more electrons come to these transition metal ions. And because of that, the surface ions have larger and larger spins. And so for nickel compound, this surface ion plays an important role, and these hoppings plays an important role. So the interlayer exchange interaction is important in this case. So here, from experiment, the Néel temperature is around 155 Kelvin, whereas the Néel temperature obtained from our first principles and Monte Carlo simulation is a bit higher than that. But our estimate is much better than previous theory. And experimentally, we find that it becomes isotropic above the Néel temperature, and there is some broad maximum after that, which is qualitatively in agreement with our case. And here's the thickness dependence from calculations. It depends somehow. But the thing is that even for monolayer sample, we observe from our calculation phase transition at finite temperature. And so how could we understand the experimental data? That was a puzzle. And the first author of our paper solved this puzzle. And this is again the polarized Raman spectroscopy data. And I said that there are two phonon peaks which is very close in energy, and their Raman tensor looks like this. And so for one phonon peak and the other slightly shifted phonon peak. And the experiment, they did XX and XY measurement. So from XX measurement, they will only observe this Raman peak, but not this one because the Raman tensor component is 0. But for XY measurement, they will observe only this Raman peak. But now we can think that because this is monolayer, all three zigzag spin directions are equivalent. And so we could think that there are some domains which have one part of it is aligned this way and the other part aligned that way or that way. So if we average over those three domains, the Raman tensor will be rotated. And if we do that, then the Raman tensor for those two peaks become exactly the same, and the XX and XY components are the same. And so for both or a few layer system, and so this is our simulated Raman spectra for XX and XY image. Even if the splitting is small, because each measurement sees one thing, they can find the difference. But for a monolayer sample, if we average everything, then each curve will see, so each setup will see both peaks, and so there one cannot distinguish where to find the splitting. So our conclusion was that Raman spectroscopy cannot resolve cannot confirm the magnetic phase transition in monolayer nickel. And so if there is some more direct experimental measurements on this single layer compound, it will be very interesting because it's related to this Mermin-Wagner theorem, to the magnetism XY system. So, and recently there has been susceptibility measurement on 2D materials. And I think that I'm not sure. I'm not an expert, but maybe heat capacity measurement can also be done. So, so this is a comparison of our calculation of the specific heat and the experiments, a few experiments. And in some cases, the TC values agree, but in this case, we know that our TC overestimates the TC from nickel compound. But by the way, different experiments don't agree with each other very well. So maybe there may be more experiment than might become. And we did some calculation on few layer sample susceptibility and heat capacity that can be confirmed by experiment. So in summary, so manganese compound has small easy access anisotropy, and there is a competition between single ion and dipolar anisotropies. And the iron compound, we have strong easy access anisotropy arising from the spin-off coupling. And this anisotropy is almost 2 orders of magnitude bigger than when we didn't include this initial configuration and the spin-off coupling property. The nickel compound has small easy access, in-plane easy access anisotropy. And it has, this compound has large interlayer exchange interactions. And because of that, it depends somewhat sensitively on the number of layers. And we predict antiferromagnetic order in single layer sample, but it needs some more experimental study to verify. So from method point of view, our study has some new elements. So we have the matrix form of interlayer and intralayer exchange interactions. And in our Monte Carlo simulations, we included the effects of orbital polarization and the dipole-dipole interactions as well. So here are the reference papers. The first four are collaboration with our experimental colleagues, and this one is the theory one. Yeah, I would like to thank my collaborators for their work and also for their slides which I used in my presentation. Yeah, Ji-Hoon did work on ion compound, and Tae-Yoon, all three of them were my students, and they're currently postdocs, and he's now in Samsung. And Tae-Yoon did a nickel compound calculation and also the anisotropy study, and Hwang did manganese compound study. And my experimental colleagues at SNU and at Seogang University Hyunsikjeong, second bar. And my students are visiting here, CFM, and they come from time to time to the IPC seminars, like Yang Jun Lee and Sun Ji Hong. And last, I'd like to thank the IPC and CFM for their support, and the offices, and Ivo for many things. Thank you very much.
Thank you very much, Cheol-Hwan. Are there questions? Okay.
Concerning this iron compound you show us, and I was really impressed that you have 2 orders of magnitude larger magnetic anisotropy that you assign to this spin orbit coupling. And my question is fairly simple. Can you get that from a total energy difference in a DFT calculation for 2 different orientation of the magnetization with a standard DFT code, including a spin orbit coupling, or not?
Yes, but so one has to start. If one start with the initial state, which is very asymmetric, then it may end up at that state. But in our case, we had to modify the occupation matrix to have a complex number so that it has it start with these
You have to play with the occupation matrix.
So simply including spin-orbit coupling may not end up at this ground state.
Yes, well, I have a couple of questions, if I can. One is a little bit, I have many questions, but I think I can meet with you later and discuss those. But one is about the role of domains on anisotropy too, because when you have domains in the crystal, when you have many domains in different directions, also you can average, and somehow your anisotropy gets smooth in this case. That's the first question. And the second question is, why not cobalt compounds? Because cobalt, you have done manganese, iron, and nickel. But if you do cobalt, you have 2 electrons in one level, and it should show a kind of Ian Teller splitting and some deformation of the ions. So then, okay.
Right. Very good question.
The first question is, what's about the domains? You have domains in the layer.
Right.
But also when you have anisotropy, if it's in plane, you average this anisotropy. So then somehow the anisotropy could be smaller than the one that you calculated. It's measuring several, because the susceptibility measurements are also global measurements and not local measurements.
I'm not sure I messed up. Sorry, I have to. Yes. You're right. Yeah. For let me answer the second question first. Okay, you're right. So yeah, for cobalt compound, it will be like these states are fully filled. Right.
Jahn-Teller distortion will allow, like you can have some Jahn-Teller distortion of the transition metal atoms and have the two spins in a lower state. You will have still, you have some splitting. It's like cobalt or chromium compounds will be something like interesting compounds too. So
Okay, so maybe the actual answer is that our experimental colleagues were more interested in these three compounds, and also there were some things that the experimentalists were not very sure about, and also we did calculations, but not from this perspective. But I don't know, it was several years ago, but I don't know, but the convergence was not easy, or there were some aspects that we couldn't understand the experiment, but I don't remember quite well.
we can discuss later.
Right, but if these two levels are filled, why there is some Jahn-Teller type? How could there be some Jahn-Teller type distortion?
Because you have two levels occupied,
Mhm.
then if you have some more splitting of the transition metal, some deformation of transition metal around these ions, will lower the symmetry, and then these two levels split, and then you have like two electrons in the lower level and one up. So then you have some distortions that are not in the other cases.
I see. By the way, this splitting already occurs because of the distortion from.
Yeah, but still you can have found some. You put cobalt, still you will find some other way to distort it.
Yeah,
But
we
it's an
can
interesting thing to look at.
see. Yeah, maybe we can discuss after
Yeah.
this. And the first question was about the domain.
Yes.
So if I remember correctly, only for that nickel compound Raman, is the way that they decide whether there is magnetism or not from the splitting of those two peaks, the domains were could change the results, but for other, for example, ion compound, ion compound, there could be, even if there is some domain of different domains, still the result will be from the Raman measurements, the result will be the same. So the peak appears when below the near temperature. So independent of the direction of the zigzag antiferromagnetism. And also for manganese compound as well, because they see the position in Raman peak, shift of the position of the Raman peak. So only in the nickel case, the domains may affect, different domains may affect the results, because there the Raman tensor is very important. There are, from the beginning, there are two peaks, but their Raman tensors may change, which is sensitive to the domain directions. So, yeah, at least in this case. Yes.
Are there other questions? Daniel?
Yeah, I have a very simple question, probably out of my ignorance of this. So you mentioned the importance of dipole-dipole interactions for some of the compounds, at least.
Mhm.
Is this a posteriori correction that you do to your model, or is something that is included in the ab initio calculation somehow?
No, we think that ab initio calculation cannot take into account that long range calculation, so we put it by hand.
And in that case, is it important how you handle things when the magnetic moments are close? I mean, how do you model this?
You mean closed shell or?
No. When they are, I mean, like if you have dipole interactions, if things are far apart, then this is no problem. But when things are located in the neighboring region, then they start to be tricky.
Right. No, we just deal with them as point dipoles, and just one of our cube interactions, which is one of our cube interactions.
And then, so then you have some maybe free parameter on how to deal with this interaction when, as a function of distance. Is that critical in any way?
Oh, actually, we don't have at least that's within that simple model. we just assume each spin is a point.
Okay.
And then we just add one of our the simple the ENM formula, apply that.
Okay, thank you.
So for thinner layers, and especially for a monolayer, it's probably important what the substrate is. So how do they measure Raman? What's the substrate, and can you actually see the effects of coupling to the substrate?
Yeah, that's a good point. Actually, yeah. So right, they use the SiO2 and the nickel compound case, which is right. The referee asked the same question, so they did experiment on SiO2 as well as HBN, but their finding, our claim was that it doesn't depend sensitively on the substrate.
Well, also, so you showed some optical data. It's pretty big gap, like 2 eV.
Mm-hmm. Right.
Is this
This one?
yeah? So this is kind of correlation gap, or these materials are just band insulated.
Okay. So people say that this is in mud insulator, this there has this upper Hubbard and lower Hubbard insulator, and both of them have the D transition metal D characters. And people say that when the chalcogen level moves up, or the transition metal level goes down, moves up, then the top of valence band is chalcogen, like sulfur or oxygen. So in this case, it's sulfur, and then they call this charge transfer insulator because I don't know, maybe optical transition will result in some charge transfer. And in this case, the transition metal ion level is even further, so that the conduction band has sulfur character. And in this case, they call it a negative charge transfer insulator. But it's strong correlation physics, so I'm not an expert.
Any other questions? I have a very quick question. So in your comparison with the Raman experiments, were you just looking at the location of the peaks, or could you also calculate intensities?
Yeah, we can also calculate the intensity using commercial software.
Okay.
Yeah. Right. Okay, so the manganese compound, the one that I showed, has intensity as well. But for the nickel compound, these two peak thing is just schematic, our toy model calculation. It's not.
So this is non-resonant Raman, so that's why maybe there is a standard package that you can use for them.
Yeah, probably.
Mm-hmm. Okay. If there are no other questions, let's thank Cheol-Hwan one more time. Cheol-Hwan is here until February, so there's plenty of opportunity to end of February.
Yeah.
Right. So, and he's in CFM, so plenty of opportunities to discuss. Yeah. Now,
Estado concertado en la ayuda y la dispersión de
Even if you split this two, they're
Well, no, okay, what does it mean? No, nothing, everything is very easy.
I was thinking. Plenty of developing calculations in these things because I was having plenty of comments, but it was mostly about the detail. But then next week I have a conference in Prague, so maybe November or November. I will be glad to.
Yes, of course. Maybe you can send me an email.
So he's scheduled.
So just because of that, he doesn't feel like but it's just a matter of arrangement.
Would you write the email list?
Andre from now. By global.
Okay.
I like bike, but very relaxed.
I like cycling, but
But these are done also as part of layers. When you change the cobalt by manganese or iron, nickel, the Heisenberg design of the couple that is AFM.
The very first one.
Here one interesting thing. They have also the domains are important. That's for the cobalt are very important because it's cobalt and isotropy is like maybe it's a good idea. That's what I say that for cobalt should have something like higher isotropy. So then this could be a good thing to discuss.
Okay. Yeah.
Thanks so much.
Very good. It's good to have this session.
I should know first about this works simplemente para yo, para verlo. But I can send it.
Did you check the question?
Yes.